In today's session, we're going to do a quick but complete recall of the most important basics that you need to know for your paper 6, along with some key tips and tricks that will help you score better in the exam. Whether you're revising at the last minute, just want to strengthen your fundamentals, stick till the end because we will be covering everything that actually matters in the ATP, especially all the types of errors, how to overcome them, some very important things just like FiducialPoint or the meniscus or sets here in the pendulum experiments. At the end, we are going to cover some common questions that cover like the errors, how to overcome the errors, the difficulties, or how to overcome the difficulties in the right? Starting from types of errors. So there are basically two types of errors. The students get confused, like whether it's a systematic error or the random error. So let's quickly discuss systematic errors are those errors which occur due to the faults in the instrument used during experiments. For example, the dead spaces in the ruler, broken edges of the ruler using an improper calibrated thermometer, or the zero error in any kind of instrument, just like ammeter or voltmeter. Okay, so what is the zero error? It occurs when the instrument gives a false reading when the true value of the measured quantity is zero. Let's starting in the practical example from the jet space in the ruler. You can see from the diagram here, like the ruler is starting zero at here, but that's in the start, that's the dead space. And if you measure from here, that may cause error in the experiment. Okay, you have to start from here. The zero error in the ammeter. The needle on an ammeter failing to return to zero when there is no current flowing through it. For example, there is no battery connected to the instruments, and still the ammeter is showing like this point here. So it means that there is an error in the uh, instrument that we are using, the ammeter. Okay, a top end balance. So if you have nothing placed on the top end balance and still it is showing some values, it means that there is an error in the top end balance. So how can you overcome this error? Like that kind of instrument that we can cover up like by making it zero or pressing the tail button. So in any other kind of experiment that we have discussed upper in the examples, so identify and change the faulty apparatus. But in the case of that, like if the thermometer is digital or the top end balance is digital, so you can just press the tail button here and make it zero before placing the instrument or the object on it. Random errors. These are basically the fluctuating errors that differ from measurements to measurements and that are caused by human reaction time or fluctuations in atmospheric conditions like temperature. And the last one that's very important, that's the parallax error. Let's discuss some of the examples from random error. The first one, let's discuss the human errors. These are caused by human mistakes. For example, incorrectly inputting the readings, responding to measurements with delays, like human reaction time error that usually we get in the simple pendulum experiment, or using the instruments incorrectly. The first and the last one, we have, no correction for that. Like you have to redo that things. But for this one, you can simply take the multiple readings and take the average value. Okay, for the human reaction time error. Parallax error, one of the most repeated one. The students that know not anything, not any error, so they come up with the one answer that's a parallax error. But we must know when there is a parallax error and how to overcome that. This is when you not place your line of sight perpendicular to the reading. And how to overcome that, like you have to see exactly perpendicular to the reading. So how can we overcome that? For example, that is an experiment from the spring, and that is the marker here, the needle marker here. So a student is watching from here, one is seeing from here, and number two is seeing from here. So the one that is reading or line of sight is exactly perpendicular to the scale. This one is overcoming the parallax error. These are reading wrongly. This one is reading here, less than the actual value. This one is reading more than the actual value. This one, the second one, is exactly reading the reading that the actual is. Okay, so there are some general measurement instruments. For example, you can see the ammeter is here. Sometimes we get the manual, or sometimes we get the digital thermometers, sorry, ammeters. So the digital ones that are perfect for that kind of any kind of experiment because they do not have the parallax errors. Okay, here we have the parallax error, we have to remove it, we have to see exactly perpendicular to the line of sight. But here we do not have the parallax error at all. If in the question there is a digital thermometer given, so you cannot mention that there is a parallax error. Remember that, okay? Now, while reading the measuring cylinder, so still that same case is here, but there is a difference here. Like we get a bubble here, okay? The sides are above and that one is below. So we have to read the bottom of the meniscus, okay? So the one that is reading at the bottom of the meniscus reading exactly, okay? Sometimes they ask that why we read the bottom of the meniscus. So you need to remember that there is very less amount of volume above, okay, here. So it's better to read at the bottom instead of reading the top, because if you read at the top, that one which is not available here, you're reading the extra content. Okay, so that's why we read at the bottom of the meniscus. There are some examples, the exact relevant examples. For example, you can see here the top one, if you read it 7.74 sorry, it's somehow 74 plus reading, but that one is 74 reading. Now moving towards a very important point. I think before then talking about set-scale, let's talk about the fiducial point, okay? Because that's a very important one nowadays. The students are asking about it again and again. So what exactly is the fiducial point? Fiducial point is simply a fixed reference marker that we place at the equilibrium position of the pendulum. That means the center point, the position where the pendulum hangs straight down when it is at rest. It could be a pen, a marker, a piece of tape, or any fixed object placed right at the center of the position. And we use it as a reference. So that every time the pendulum swings and passes through the center point, we count it accurately. Okay. So the question comes like, why do we use it? How do we use it? That's a pendulum kind of experiment from spring. This oscillating up and down. So when it was not oscillating, it was at rest position. So we marked a fixed point here with the putty. Okay, so that we have to get the time period exactly whenever it's passing through the center. Okay, there are some examples. The first example we have already discussed, the real-time example up here. The second one is here. Sometimes we use the set-scale as well for that purpose. Okay. Set-scale may be used to measure exactly the reading here on the scale, but it may be worked as fiducial point. You can use it as, but instead of that, use a marker here. All right. So to discuss more about it, we can simply do one more activity. Just give me a second. Let me take you to a point here. Yeah. So see, that is an experiment in which we can oscillate the spring, okay? So before oscillating, let's see its rest position, okay? So I can induce a fixed point, okay? That's fiducial point. That is marking exactly at its rest position where we can read it, okay? So now if I release it from here, so it's easy for me to read whenever it's passing through this point. Okay, that's why we use the fiducial point. The same we can use, just give me a second, in the simple pendulum experiment here. Okay, so it's at rest. So we have to mark it here, we have to place a pin here, or we have to mark with a marker here, it's at its rest position. Okay, here I have a fixed dotted line here. It's working for the same nature. Okay, so whenever it's passing through here, why we use it? Like whenever it's passing through here at the center, it has a maximum speed. Okay, so it's easy for me to mark or press the stopwatch. For example, the stopwatch. So I can exactly press when it's moving from center. Okay, so I can take the multiple readings, and whenever it's passing here again, so I can press it again. Okay, right? So let's move back to the set scale. Okay, we have left the set scale before. So what are the set scales? Okay, the set scale is basically triangular shape instrument from your geometry, and it has a perfect 90-degree angle. Or we can assure that any object, or for example, our scale is perpendicular to the surface, right? So in your ATP practical exam, you will most likely to be given one or asked about how and why it is used in the pendulum experiment. So when we set up a pendulum, the string must hang perfectly vertical, perfectly straight down. If the string is tilted even slightly, the length we measured will not be accurate. And since the period of the pendulum depends on its length, any error in length will affect all of our results. So we use the set scale to confirm that the string of the pendulum is hanging at exactly 90 degrees to the horizontal surface, meaning it's perfectly vertical. This ensures our length measurement is correct and our experiment is reliable. Okay. And another thing is that, for example, for this experiment, so we can take exactly like if it's at rest and we have to measure the length here. So this ensures that if we do not have a pointer here, this ensures that what is the reading here. Okay, and it sits perfectly on the surface of the scale. Right? I hope this is also done here. Okay, another use of this is like whenever you have to measure the diameter of the sphere, or you have been given the multiple marbles and you have to measure the diameter. So what we can do, like we can place the object in the center and we can take the reading at the very end. Okay. So if we do not have the center, we have to take the radius, whatever it is, we can take these readings and we can take half of it, for example, for that purpose. That's why we are using the set scale so that we can exactly take the reading. As this point that we have to read is above or away from the measuring instrument. Okay, so that's why we can use set scale for this purpose as well. Now move towards some of the very important questions from the past papers, and one by one we are going to attempt those questions. For example, the first one is starting from the investigate the effect of length and mass on the period of a simple pendulum. And for example, they ask about the precautions to improve the accuracy or give more reliable results. So there are certain points you may be asking about maximum 2 points. Okay, so you can use as per your as you remember or as per the given condition of the question. Sometimes, like it's very important, like you do not need to on the fan, so there are no air currents in the place. That's a very casual one or usual one. Take the time of the number of swings and divide the time measured by the number of the swings to get teeth. Sometimes it's already given in the above scenario somewhere in A, B, or C point. So sometimes we have to neglect that. We cannot repeat it. You repeat it, you're not going to get any mark. Repeat and take the average. That's a very important one. For example, for the first 20 oscillations, you take the oscillations for the same length or for the same mass or for the same amplitude. You have to take it again and then again, like take 3 readings and then take the average. This will reduce the human reaction time. Okay, that's very important. Like look perpendicular to the ruler when measuring the height, or use the set scale as horizontal reference. Okay, for measuring the length of the simple pendulum. Meter rule should be close to the pendulum, or measure the length from the center of the mass of the ball. Okay, the common questions are why measuring time of 20 swings oscillations rather than one swing is more accurate. And the result for this is to reduce the effect of reaction time, or to reduce the error. A time of one swing is too small to be measured. Okay, because there will be huge reaction time error. Why measuring the time of 20 oscillation is not suitable? Sorry, 200 oscillations not suitable. That's very simple. Like in real life, the pendulum is stopped after like 40 or 50 or 60 oscillations. So for that 200 oscillations, the pendulum is stopped. Or you may lose counting, like you have to count at the center, so you may lose counting. Okay. So just a practical reason why the result obtained from experiment is different. Student did not react quickly when the pendulum started. So human reaction time again, or difficulty to measure the length from the center of the ball. Sometimes it's difficult for the students to measure exactly at the center of the ball. So this may be a reason sometimes, okay? So just improvement to the experiment. So there, depending upon the question, there may be certain points, like the first one is repeat and take the average if it's not given up, and usually it's not given. Use different lengths, okay, and use fiducial mark. And usually the first and the last one is very important. Now moving towards another experiment, and that's about the moment, okay, the balancing one. So we are going to talk about the difficulties and how to overcome it. Okay, there may be the first question: balancing the ruler above the pivot. It's it's difficult for the students sometimes. Okay, so for that we have to repeat for the several times until it balances. Okay, the mass slips over the ruler. Okay, that's usual. Sometimes that's a question. So for that, what we can do, we can take a putty or something else, like very small quantity, that we can stick it with the mass on the ruler. Or another thing is that if there's something to bind it from above, you can mark or bind it from the string and put it here. That may ensure that what's the center of the object here. It's easy to read from here at that time, and it's easy to hang it here. Okay, the center of mass of the cylinder may not above the correct mark. Exactly, that's the point. Measure the diameter of the cylinder. Okay, calculate the radius. Adjust the cylinder above the correct mark so that on the side of the cylinder, the mark x minus r and x plus r, the exact example is there. For example, so mark the center. Okay, take the radius, or you can mark it here exactly. So what you can do, like take the reading and take x minus r and x plus r simply and find those points here. For example, the points are like it's 74 and 70. So take these points 74, 70. So it will be exactly at the 72. Right? Precautions to improve accuracy or to give more reliable results. So in a similar experiment, this experiment, repeat and take the average. It's a game, okay? Look perpendicular at the scale of the ruler while taking the readings to avoid parallax error, or take the range of the masses. Okay, do not depend on only one single kind of masses. The common questions are, what is the mass of the ruler? Okay, usually students do not remember it, so it's from 100 to 200 grams. Where is the position of the center of the mass? It is the point at which the meter rule balanced above the pivot. Okay, so it's usually at the center. Okay, but instead of mentioning, if it asks state it, then state for a uniform meter rod it's 50 or about 50. Okay, but the common one is that, like, where the meter rule balanced above the pivot. Right. Let's move towards the spring experiment or the Hooke's law, difficulties and how to overcome them. For example, the student is investigating the Hooke's law for a spring. The clamp, retort, stand might topple. Okay. To overcome that, use small loads. Spring might stretch or spring too weak. To overcome this, use loads that do not unstretch the spring. Overstretch the spring. So usually it's recommended in that whenever you use it, quickly take off the weights. Or if you have to use, do not use heavy weights. Okay, use the weight that are smaller or for which the spring is, oscillating easily and it's not overstretching. Possible cause of inaccuracy in spring experiment or the Hooke's law is spring extension is not uniform with load. Okay, if you are changing not uniformly, so the extension will not be uniform. Spring exceeds the limit of proportionality. Sometimes this happens, the spring is very weak, or if you put on heavy weight with that, so it easily exceeds the limit of proportionality. Precautions of safety. Take care with masses and think the hanging masses would fall if the spring snapped. Okay, that's a very if you have something to hold on the weights, so it's a common one. Okay, or if you move it fast, so there may be chances that it may be toppled. Precaution to improve accuracy or to give more reliable results. Look perpendicular to the scale every experiment in which you talk about the measurements, you have to take the reading. You have to avoid the parallax error. Wait until the spring stops vibrating. Okay, not you are just leaving it. You not start taking the reading from there. You have to wait like after 1 or 2 oscillation, it may stop vibrating. So you can take the reading from there. Start taking reading from there. Always measure from the same point of spring. Ensure the rule is vertical. Use horizontal lead. That's the fiducial point again. Bench surface must be horizontal. That's a very important point for this experiment. This one and as well as for the simple pendulum. The surface should be horizontal, straight. At least 5 floats of each spring if producing a graph. Like if you have to take a graph, then you have to take 5 floats for each spring. Okay. And how can you improve the accuracy? By clamping the meter rule in place and then using the set scale to make the length or extension measurement. It should be straight. It should not be moving. And use the set scale to make sure the clamped ruler is vertical in relation to the bench. Here you're using the set scale again and again. Use set the clamp ruler at 0 centimeter when no masks are added, and so read the extension directly. So instead of starting from 7 or 8, what's the actual length? So you should place it at 0, like move the ruler down, and so that the pointer is at the 0 centimeter, and then start taking the reading. The extension will be directly starting from 0. All right, with that, we are ending today's session here. Let's meet again with the next, like the thermal one. Okay. All right. Take care.